Okay, in today's lecture, we're going to cover the first part of the section 1.9 material on the matrix of a linear transformation. So in our previous section, we had talked about transformations from a space Rn to Rn. And the types of transformations that we were looking at were called matrix transformations, where the transformation T acts on a vector X by applying a matrix A to that vector through matrix manipulation or matrix multiplication. So we had seen in the previous section that every matrix transformation is linear. And in this section, we will see that, in fact, every linear transformation from a space Rn to Rm can be thought of as a matrix transformation. That is something where x, a vector in Rn, is mapped to A times x. So not only is every matrix transformation linear, but every linear transformation from Rn to Rm can be considered as a matrix transformation. So if we're interested in determining, well, for a given transformation, what is the matrix A that would describe that transformation, then we could determine that matrix by looking at the images of the columns of what's called the identity matrix under the given transformation T. And we had seen this a little bit in the previous section 1.8, that if we look at the image of particular column vectors, we can find the image of any vector, and we'll see here that we can define a matrix which would describe a given linear transformation. So to introduce this concept, let's consider working with the columns of what is known as the 2x2 identity matrix. So we have these column vectors, which we denote as E1 and E2. Those are 1, 0, and 0, 1. And we had seen these E1, E2 vectors a little bit in the last section, 1.8. And I claim that these two vectors are columns of what's called the 2x2 identity matrix. So what exactly is this 2x2 identity matrix? So it is the matrix which has these vectors as its columns. So my first column is the vector E1, 1, 0, and my second column is the vector E2, which is 0, 1. So we have this 2x2 matrix, which is called the identity matrix, and it's typically denoted as capital I. And as we move through the remainder of the course, we'll see this identity matrix come up a lot. We'll discuss it in much more detail at the beginning of our chapter 2 material. So let's consider those two vectors, which are the columns of this identity matrix. And let's suppose that we have a transformation T, which we're told is a linear transformation from the plane R2 to space R3. And the images of these E1 and E2 vectors are T of E1 and T of E2, which are the given vectors here. So in part A of this example, we are asked to find a formula for the image of an arbitrary vector x in R2. So if we know what the image of these two vectors E1 and E2 are, we should be able to find the image of any vector in the plane. So let's see how that's going to work. Let's start by considering an arbitrary vector x in the plane. So it's a two-dimensional vector whose components I'm going to call x1 and x2. Now any arbitrary vector in the plane can be written in terms of E1 and E2 in the following way. I could take x1 times the vector 1, 0 to get x1 in my first component, and then plus x2 times the vector 0, 1 to get x2 as the second component. but we recognize this as x1 times the vector e1 plus x2 times the vector e2. So here, any vector we see can be written as a linear combination of these e1 and e2 vectors. So these e1 and e2 vectors are what are sometimes called the standard basis vectors for the plane, and we'll discuss basis vectors in more detail a little bit later in our course. So if we want to find the image of that arbitrary vector x, well, x, we just said, can be written as a linear combination x1 e1 plus x2 e2. But t, we were told here, is a linear transformation. So because t is linear, t of this linear combination of vectors is the same as x1 times t of e1 plus x2 times t of e2. That was exactly what it means for a transformation to be linear, is that the transformation of a linear combination of vectors is the same as the linear combination of the transform of those vectors. But now we know what the image of t1 was equal to. Here, t of e1 was the given vector in the problem statement, 3, -5, 1. Plus, we have x2 times the image of e2 under the transformation t was given in the problem statement as -1, 7, 2. So if we write this as a single vector, we have 3x1 minus x2, -5x1 plus 7 times x2, and 1x1 plus 2x2. So for any vector, x1, x2, in the plane, the transformation of that vector, or the image of that vector under this transformation t, is given by the equation that we just found here. So this is a linear transformation, and I claim that we can express this in terms of a matrix transformation. So in part B, we are asked to find a matrix capital A such that this transformation T can be considered as a matrix transformation where a arbitrary vector x is mapped to A times x. So here, let's think about how to define our transformation T of x as a matrix transformation, something of the form A times x. Now in our previous part of this example, part A, we showed that T of x can be written as a linear combination of these two vectors. So that vector equation I can rewrite as the following matrix equation. Instead of writing it as that linear combination, I can write this in matrix form as the matrix A, whose first column is 3, -5, 1, and whose second column is -1, 7, 2. And then I'm multiplying by some arbitrary vector x in the plane, whose components are x1, x2. So recall that we can rewrite those vector equations as a matrix equation, and so we have the following description for that transformation T. We have some matrix A 3x2 matrix, times our vector x, which is 2x1, which is going to give us a vector in space. So this matrix A describes this linear transformation T. So one thing that I want to stress in this first example is notice that the columns of this matrix A are exactly the two vectors, 3, negative 5, 1, and negative 1, 7, 2. And those two vectors were the images of E1 and E2 under that transformation T. So our matrix here, or our matrix A, which describes the transformation T, has columns which are given by the images of those E1 and E2 vectors. So we could ask the question, well, would that always be the case? And the following theorem, which is Theorem 10 from your textbook, says that that is indeed the case. So this theorem tells us how to find the matrix associated with a linear transformation. So here's what it says. Let's suppose that we have a transformation T from Rn to Rm, which is a linear transformation. Then this theorem says there exists a unique matrix A, so that is one specific matrix and only that one, such that this transformation, T, acting on a vector x can be described as a matrix transformation, just multiplying that vector x by a given matrix A. And A is specifically the m by n matrix, where the jth column of that matrix is the vector T of Ej, where Ej is the jth column of the identity matrix in Rn. So in our first example, we were looking at the 2 by 2 identity matrix. So we only had two columns, so the vectors E1 and E2. If we're looking at a transformation that's mapping from Rn, then our identity matrix in Rn has n columns, which we would denote as E1, E2, up through En. And if we take the transformation of each of those columns, then take the transformation of each of those columns as the columns of a matrix A, that matrix A is the matrix describing that transformation T. And this matrix A, which is describing our transformation, is called the standard matrix for that linear transformation T. So what this theorem says in summary is if we're trying to find a standard matrix to describe a linear transformation, we need to find the images of these column vectors of the identity matrix, T of E1, T of E2, up through T of En, and then we put those images in the columns of a matrix, and that's the standard matrix that we're after. So as an example to illustrate this theorem, let's suppose that we have a transformation T from space R3 to the plane R2, and we're told this is a linear transformation where the image of the columns of the 3 by 3 identity matrix, E1, E2, and E3, are given here. Where E1, E2, and E3 are the columns of the 3 by 3 identity matrix. So in this example, since we're mapping from R3, we're looking at the 3 by 3 identity matrix. So in this case, we would have 3 column vectors of the form 1, 0, 0, 0, 1, 0, and 0, 0, 1. And these columns are what we're calling E1, E2, and E3. So those are known as standard basis vectors for space, or for 3 dimensions. So we are asked then to find the standard matrix for that transformation T. So using our theorem, this new theorem, Theorem 10, the standard matrix A that we're interested in is the matrix whose columns are the images of of E1, E2, and E3 under this transformation T. So here A would have a first column of T of E1, which we were given as 1, 3. The second column is T of E2, which is 4, negative 7. And our third column, T of E3, is negative 5, 4. So this would be the standard matrix for that transformation. So again, this example illustrating that as long as we know the image of these so-called standard basis vectors, E1, E2, or maybe E1, E2, E3, depending on what space we're mapping from, we can find the standard matrix. So let's look at another example, maybe a little bit trickier. In this next one, we are asked for the standard matrix A for the dilation transformation T of x is equal to 4 times x, where we're taking vectors x in the plane. So recall that a dilation transformation is a transformation where you multiply your vector x by some scalar, which is greater than 1. In this case, we're multiplying by 4. And we're looking at vectors x in the plane, so two-dimensional vectors. So using our new theorem, Theorem 10, we know as long as we can find the image of these basis vectors, E1 and E2, then we can find our standard matrix. So since we're looking at vectors x in the plane, we just need E1 and E2. Those are the first columns, first two columns of the 2 by 2 identity matrix. And if we can find the images of those vectors, then we have our standard matrix. So let's look at the images of these. T of E1, well, our transformation is a dilation where T of x is just 4 times x. So to get T of E1, we multiply the vector E1 by 4, giving us 4, 0. And the image of E2 under this transformation T would be 4 times 0, 1, or 0, 4. So our standard matrix for this transformation A would be the matrix which has these images as its columns. That is the matrix whose first column is 4, 0, and whose second column is 0, 4. All right. So these first few examples, along with Theorem 10, illustrating that to define a linear, or the matrix of a linear transformation, we just need to find the image of these basis vectors, E1, E2, E3, and so on. Okay, so let's look at some other examples of common linear transformations in the plane, at least. So in our next example, we're considering the transformation T from the real plane to itself. And this is going to be the transformation that rotates each point in the plane counterclockwise about the origin through an angle of theta. And for that transformation, we want to find the standard matrix for that transformation. Okay. So based off our previous examples, well, we're mapping from the plane. So since we're mapping from R2, or since the domain of our transformation is R2, we're going to look at the standard basis vectors E1, which is 1, 0, and E2, which is 0, 1. Those are the first two columns of the 2 by 2 identity matrix. And we need to be able to find the images of these vectors under this transformation. Now here we're given sort of a geometric description of what this transformation is doing. So let's see if we can use that to find the images of these two vectors. So let's consider sketching this transformation in the x1, x2 plane. So looking at our first vector, E1, we have the vector 1, 0. So its position vector representation would have its initial point at the origin, and we're taking the vector E1, which moves 1 unit to the right and 0 units upward or downward. Now for that vector, we rotate by counterclockwise by an angle of theta, and we need to find what the image of that E1 vector is. So if I have its representation as starting at the origin, to get the components of that vector, I need to know what the terminal point of this vector is. Some point, let's call it x1, x2. So to find the coordinates for that point, well, I can think about the right triangle, which is formed by rotating the vector E1 through by that angle theta. And I see that x1 would be the horizontal distance I've traveled, and x2 is the vertical distance I've traveled to get to that terminal point. So using trig functions, well, here we had a vector of length 1, so when I rotate it, it still has length 1. So to find x1, well, x1 could be thought of as the cosine function. Cosine of theta would be the ratio of the adjacent edge, which is x1, to the length of the hypotenuse, which is 1. So the image of this E1 vector under this transformation would be cosine of theta for my x1 coordinate, and then x2, the vertical distance which I've traveled, would be sine of theta. Now, to get the image of E2, well, let's think about the E2 vector. So E2 is the vector 0, 1, so its representation starts at the origin and travels 1 unit upward. And I'm taking that E2 vector, and by this transformation, I am rotating counterclockwise by an angle of theta. So this vector represents the image of E2, and to find the coordinates for that vector, or the components, I need the terminal point of that vector, x1, x2, where x1 is going to be my horizontal distance I've traveled, x2 the vertical distance. So if I think about the right triangle formed by that angle theta, to get the vertical distance traveled, my horizontal distance traveled, let's say x1. X1 is the edge opposite of the angle theta. So I would be looking at sine of theta for that value. But since we're in the second quadrant, x1 is then negative. So I've got negative of sine of theta. And my y value, or x2 value here, the vertical distance traveled would be the leg adjacent to that angle theta, which would be cosine of theta. Here positive, since we're in quadrant 2. We've got a negative value for x1, a positive value for x2. So once I have the image of E1 and E2 under this transformation, then the standard matrix A for that transformation would have a first column of the image of E1, which was cosine theta, sine theta. And the second column would be the image of E2, that is negative sine theta and cosine theta. So this matrix represents a counterclockwise rotation about the origin through an angle of theta. So if we had a specific value of theta, or a specific angle that we were rotating by, we could substitute that into these trig functions to find the specific matrix describing that angle. So let's look at an example of that. Suppose that we have a transformation T from the plane to itself, which is the transformation which rotates points now in the clockwise direction about the origin through an angle of pi over 4 radians. So in the previous example, this matrix that we found was describing a counterclockwise rotation about the origin through an angle of theta. So in this next example, if we're looking at a clockwise rotation, we're just moving in the opposite direction. So we could think about a negative value of theta there. So to describe this transformation, we're looking at a counterclockwise rotation by negative pi over 4 radians, or similarly, a clockwise rotation by positive pi over 4 radians. So to reverse the direction of rotation, we just change the sign of theta. So based off what we found in our previous example, the standard matrix that we're looking for is given by cosine of theta, so cosine of negative pi over 4, sine of negative pi over 4 for our first column, then negative sine of pi over 4, negative pi over 4, and cosine of negative pi over 4. So let's see what we have. Our matrix A. So cosine of negative pi over 4, since cosine is even, that's the same as just cosine of pi over 4, which is 1 over root 2. Sine is an odd function, so sine of negative pi over 4 is the same as negative of sine of pi over 4, so that's negative 1 over root 2. And then in our second column, we're just changing the signs of values that we've already found. So I would have a positive 1 over root 2 and 1 over root 2. So this would be the matrix A describing that transformation. Okay. So we see in these first several examples that for linear transformations, as long as we're able to find the image of those so-called standard basis vectors, E1, E2, E3, and so on, under our transformation, then we can find the standard matrix describing that transformation. So we've done a few examples here, finding the standard matrix for different sorts of linear transformations in the plane. And rather than look at many different examples to generate all the different standard matrices for these common transformations, we'll just describe them in a table here. So the following tables, which we'll consider, illustrate the form of the standard matrix for several common geometric linear transformations in the plane. Common geometric transformations that we're going to consider are reflections through different lines, contractions or expansions of a vector, shears, which we considered in the last section, and projections. So as we're moving through these tables, let's keep in mind to generate the standard matrix for the given transformation, we're looking at the columns of the 2 by 2 identity matrix, 1, 0, and 0, 1. So those columns are what we were calling E1, and E2. And we're wanting to see what happens to each of those columns under the given transformation. And the transformations that we're describing here will be of the form T of x is equal to A times x. So we're trying to find the matrix A, describing that transformation. All right. So in our first table, the transformations which we'll consider are reflections. So there are several different reflections we can consider. The first would be reflection through the x1 axis, or the horizontal axis. So let's look at how we would get our standard matrix here. So geometrically, to get a reflection about the x1 axis, well, if we were to look at the vector E1, its reflection about the x1 axis is itself. So the image of this vector E1 under reflection about the x1 axis is itself 1, 0. Now if we look at the vector E2, which is 0, 1, when we reflect that vector about the x1 axis, we get the vector moving in the exact opposite direction, the negative of E2. That is the vector 0, negative 1. So our standard matrix for that transformation is the matrix shown here. So let's look at another one. Let's say that we're considering reflection through the x2 axis. So the image of E1, if we reflect through the x2 axis, or the vertical axis, we would get the negative of E1. And the image, so that is negative 1, 0. And the image of E2, well, E2, if we reflect about the x2 axis, would be itself. That is still 0, 1. All right. So here we have matrices for reflections about the x1 or the x2 axis. Now, let's consider for our next one, reflection through the line x2 equals to x1. So let's consider a different figure here. Suppose that we have, for points in the plane, say the x1, x2 plane, we have a line given by x2 equals x1. That is the line of slope 1 passing through the origin. So if we consider E1, the vector shown here, and we reflect that vector about this line, we would get exactly the vector E2. So here, E1 would map to E2. So our first column, 1, 0, becomes the second column, 0, 1. And if we were to look at the image of E2 under this transformation, that is reflection about this line, we would get exactly the vector E1. So our second column of the identity matrix, 0, 1, is transformed to 1, 0. All right. Okay. So let's look at some other examples. Say that we are interested in reflection through the line x2 is negative x1. So that would be the line of slope negative 1 passing through the origin. So if we look at the image of the first vector, E1, under that transformation, reflecting about that line would give us the vector 0, negative 1. That is moving from the origin 1 unit directly downward. And the image of E2 by reflecting about that line would give us the negative of E1. That is negative 1, 0. So we have the following standard matrix for that reflection. And then our last reflection is reflection through the origin. So for reflection through the origin, let's say that we have in the x1, x2 plane some point, well, let's just look at the image of our basis vectors rather than a specific point. So for E1, if we reflect through the origin, we would have the vector negative E1. So we would have the vector negative 1, 0. And for the basis vector E2, the reflection about the origin would give us negative E2. So it transforms to 0, negative 1. All right. So here we have these standard matrices for different sorts of reflections. I'll mention as we go through each of these tables, I'm illustrating a little bit geometrically with a rough sketch, but in your textbook, if you look at these tables given in the text, they have very high quality figures illustrating what these different reflections and transformations look like. Okay. So the next type of transformations, which we'll consider, are examples of contractions or expansions. So the first one that we'll look at is a horizontal contraction. So a horizontal contraction would be stretching our vector in the horizontal, or compressing or contracting our vector in the horizontal direction. So our first basis vector, E1, let me sketch it here, would be mapped to, so this vector is 1, 0, and it is mapped to a vector k0, where k is some constant between 0 and 1. So we're shortening the length of that vector. It gets mapped to some vector which is a fraction of the length of E1. And E2 is mapped to itself. 0, 1 is mapped back to 0, 1. So we're only compressing or contracting our vectors in a horizontal direction. So this is a so-called horizontal contraction. We can also define similarly a horizontal expansion if our first vector E1 is mapped to k0, where k is a constant greater than 1. So that is if we are making E1 a longer vector under the transformation and E2 is mapped to itself, then we're stretching our vectors only in a horizontal direction or expanding them. So we have a so-called horizontal expansion. Now, in a similar way, we could define a vertical contraction or expansion by leaving our first vector, E1, alone, that is mapping 1, 0 to itself, and then taking the E2 vector, 0, 1, and mapping it to 0k, where k is either a constant between 0 and 1, in which case we are shortening the length of E2 and we have a contraction, or we are making E2 a longer vector, in which case we have an expansion. Now, in the next couple of tables, we'll discuss some other sorts of transformations that we would see. In Table 3, we'll discuss shears, which we saw an example of in the previous section. So in the first case, we have what's called a horizontal shear, where the vector E1 is mapped to itself, and the vector E2 is mapped to, which was 0, 1, is mapped to K1. So that is, we're adding our K times our first column to the second column. Or equivalently, we're adding K times the second row of the identity matrix to the first row. Alternatively, we can define a vertical shear by leaving the E2 vector alone and transforming E1, which was 1, 0, to the vector 1K by adding K times E2 to E1, or equivalently adding K times the first row of the identity matrix to the second row. So recall that a shear, we saw an example of a horizontal shear in the last section, where in the x1, x2 plane, let's say if we had a box whose edges were given by these basis vectors E2 and E1. So we have a little unit square, a 1 by 1 square. We would be mapping for a horizontal shear E1 to itself, and E2 gets mapped to this vector K1. So its vertical direction is the same, but its horizontal direction has been changed to a factor of K. So here we have K by 1, so our image of this E2 vector is the following. Image of E1 is itself. So we have the image of this little square becomes a parallelogram. So this would be an example of a horizontal shear, a shear which takes a unit square to this parallelogram that's been shifted horizontally. In a similar way, we could describe a vertical shear. And in our last table, we'll discuss the standard matrix for projections. So we'll start with a projection onto the x1 axis, where we take the image of the vector E1 onto itself, and the image of E2 onto the 0 vector. So let's see how this works. So here, if we have in the x1, x2 plane, our vector E1, which is 1, 0, and we were to project that onto the x1 axis, well, since this vector lies on the x1 axis, its projection would be itself, 1, 0. Now, if we look at the vector E2, the projection of E2 down onto the x1 axis would consist of just a single point, the origin, or the 0 vector here. So in general, for any point, I'll maybe use a different color here, for some point, let's say AB in the x1, x2 plane, the projection onto the x1 axis gives us the point A0. So we're just projecting upward or downward directly onto the x1 axis. So we take our second component and make it equal to 0, that is the x2 coordinate, and we take the same x1 coordinate. Now, in a similar way, we can define projection onto the x2 axis, which is the vertical axis, by mapping E1 onto the 0 vector, and the image of E2 would be itself, since E2 lies on that x2 axis. All right, so we've got the standard matrices for different common geometric transformations in the plane described in this table. And using these standard matrices which we found, we can define standard matrices for other related transformations which might consist of one or more of these operations together. So as an example, we could consider, for instance, a transformation which consists of a horizontal shear, which is then followed by a reflection about the line x1 equals to x2. So if we have a transformation that is taking vectors and applying more than one of these basic transformations, we could describe those by looking at a composition of these transformations. So as an example of this, let's consider a transformation T from the plane to itself, which consists of first reflecting points through the horizontal or x1 axis, and then reflects that point or the corresponding points through the line x2 is equal to x1. So we want here the standard matrix A for that transformation. So let's think about how to find this. So let's think about the first part of this transformation. Here, first we have reflection through, or reflection about, the x1 axis. And this transformation is given by let's call it T1 of x for the first part of my transformation, which is a matrix transformation. It's going to be some matrix, I'll call it A1 times my vector x, where A1, the matrix which describes that transformation, or the standard matrix for that transformation, looking back in our table, would be the matrix 1, 0, 0, negative 1. All right. Now, the next part of our transformation is reflection through the line x2 is equal to x1, which is given by, let's call it T2 of x, which is some matrix A2 times x, where the standard matrix A2 for that transformation, looking back at our table, is 0, 1, 1, 0. So if I want to accomplish both of these transformations in a single step, I would be looking at the composition of these two transformations, T1 and T2. So let's consider the following. Here we're moving from R2 and I'm taking some superscript 2, R2, and I'm taking some vector x in the plane, and I'm applying first a transformation T1 to get another vector in the plane, R2, which would be A1 times x. Then I'm applying the next transformation, which is given by T2, which gives me another vector in the plane, and the transformation T2 is a matrix transformation where we multiply by A2. So we have A2 times A1 of x, and the transformation that I want is the transformation T, which is given by, or let's call this T of x, which is a matrix transformation, A of x. And I need the matrix A which accomplishes this. So the matrix that performs both operations at once, we see here, is the matrix A2 times A1. We're applying that to this vector x. So here we're going to let the matrix A that we're interested in equal A2 times A1. So here A2 was 0, 1, 1, 0. And we're multiplying by the matrix 1, 0, 0, negative 1. Which gives us the matrix 0, negative 1, 1, and 0. So this is the matrix that I'm after. Now, in this last step, okay, you might ask, well, how did you get that matrix here? For the textbook that we're using in our course, the order of the material is a little bit finicky. It doesn't make a lot of sense because in this section we need to know how to multiply two matrices, but we haven't discussed matrix multiplication yet. Only multiplication of a matrix times a vector, not the product of two matrices, which we're going to introduce in chapter 2. So intuitively here, well, how do we know how to multiply two matrices? Well, we would consider what the matrix A2 is doing to this matrix A1. So we start by looking at the matrix A1 and the matrix A2. Let's think about how the matrix A2 is being applied. So if we think about the matrix A2 in relation to the identity matrix, a little scratch work at the top here, recall the identity matrix is 1, 0, 0, 1. And we can see that A2, which was the matrix 0, 1, 1, 0, is obtained by interchanging those first two rows. So swapping row 1 and row 2. So in order to apply the matrix A2 to the matrix A1, we're going to take the rows of A1 and interchange them. So my second row, 0, 1, becomes the first row, and my first row, which was 1, 0, becomes the second row. Now in chapter 2, when we define matrix multiplication, we can get this product a little more easily, but for now we have to think about it sort of intuitively. So let's look at another example. In our next example, we are considering a transformation T from the plane to itself, which is given by first rotating points in the plane by 3 pi over 4 radians counterclockwise about the origin. And then we are reflecting that those points through the vertical x2 axis. So we want the standard matrix A for that transformation. So let's break it down into pieces again. So again, first, the transformation is rotating points by 3 pi over 4 radians counterclockwise. So let's say rotation counterclockwise by an angle of theta equals 3 pi over 4 radians is given by a transformation T1 of x, which can be described by a matrix A1 times x, where A1 would be the matrix whose first column would be cosine of theta, so that is cosine of 3 pi over 4, and sine of theta, 3 pi over 4. We had seen that rotation matrix in our earlier example. And the second column is negative sine of 3 pi over 4. And cosine of 3 pi over 4. So let's see what we have for that matrix. So to find these trig values, well, you can either have the unit circle memorized, or if you want, you can sketch the reference triangle in the x1, x2 plane. So by rotating an angle of 3 pi over 4 radians counterclockwise, we construct a right triangle whose lengths are lengths of the adjacent edges are 1 and 1 and root 2, and since we're in quadrant 2, our x component is negative. So cosine of that angle is going to be negative 1 over root 2. Sine will be 1 over root 2. So then the negative of sine of that angle is negative 1 over root 2, and cosine is, again, negative 1 over root 2. Now the next step in our transformation is reflection. So next, our reflection through the x2, or the vertical axis, is given by T2 of x, which is a matrix transformation A2 times x, where A2 is the matrix negative 1, 0, 0, 1. So the transformation that we're interested in, which performs both of these operations, would be T of x, which would be the composition of these two transformations, T2 of T1 of x, which is given by A2 times A1 of x, when I first apply A1 and then apply A2, which I can then describe as a single matrix transformation A times x, where this matrix A is the product of A2 with A1. So here A is A2 times A1, where A2 was negative 1, 0, 0, 1, times A2, which was negative 1 over root 2, 1 over root 2, negative 1 over root 2, negative 1 over root 2. So let's see what this leaves us. So we have, for the product of these two matrices, 1 over root 2, 1 over root 2, 1 over root 2, and negative 1 over root 2. So this would be the standard matrix for the indicated transformation. Now again, how could we see this matrix product by comparing or without the formal definition of matrix multiplication? Well, let's see what the matrix A2 is doing in relation to the identity matrix. So A2 takes the identity matrix I, which was 1, 0, 0, 1, and we can see it multiplies the first row by negative 1. So to get this product, I'm going to take the first row of A1 and apply the matrix A to it. I'm going to take the negative of that first row. So I get positive 1 over root 2 for both entries. And the second row of A2 is the exact same as the second row of the identity matrix. So when I apply that to the matrix A1, I leave my second row alone, and I get the following result for my product. Okay. All right. So we now know how to construct a standard matrix for matrix transformations which consist of a composition of maybe multiple linear transformations together. So as another type of example, let's suppose that I have a formula for a given matrix transformation, and I want to find the standard matrix for that transformation. So here we are supposed to show that the transformation T from R2 to R4, which is defined by taking T of a vector in the plane x1, x2, which gives me a four-dimensional vector whose first component is here, second component is here, third component is 0, and our fourth component is x2. So we want to show that that transformation is linear by finding the matrix which implements that mapping. So in order to find that standard matrix, I need to look at the image of those standard basis vectors under this transformation. So here, looking at T of E1, we'll recall E1 is the vector 1, 0, here just written as a point x1, x2. And let's see what the image would be. So the image of this, using our formula, well, our first component is given by 2x2 minus 3x1. So that gives us a negative 3. Second component is x1 minus 4x2, so that is 1. Our third component is always 0. And our fourth component is x2, in this case 0. And the image of E2 under this transformation, well, E2 is the vector 0, 1. So the image of that here, let's look at our first component. First component is 2x2 minus 3x1. So here that gives us 2. Our second component is x1 minus 4 times x2. So here we have a negative 4. Our third component is always 0, and our fourth component is x2, which was 1 here. So by using Theorem 10, the standard matrix for this transformation would have a first column given by the image of E1, so that is the column negative 3, 1, 0, 0. And the second column of A would be the image of E2, which we found to be 2, negative 4, 0, 1. So we've shown that this transformation is linear by finding a matrix which implements that transformation. So let's consider another problem, sort of similar. Suppose that we have a transformation T from the plane to space, and this, we're told, is a linear transformation where T takes a point or a vector whose components are x1, x2 in the plane, and gives us a three-dimensional vector whose first component, second, third component, and third component are given here. And for this transformation, we are asked to find a vector x such that the image of that vector x is equal to the vector negative 1, 4, 9. So in order for the image of a vector to be the indicated vector, we need the components to be equivalent. So the first component of the image of any vector is x1 minus 2x2, which we know has to equal the first component of the given vector, negative 1. The second component of the image of any vector is given by negative x1 plus 3 times x2. So to have this vector as the image, we need that second component to be 4. And then the third component, which is 3x1 minus 2x2, has to equal this third component of the given vector, 9. So we have a system of linear equations here, and to solve this, we could think about using an augmented matrix. So I'll say the corresponding augmented matrix is the following. So my first row is 1, -2, -1. My second row is -1, 3, 4. And my third row is 3, -2, 9. So to simplify, I could first take row 2 and add row 1 to it. So my first row remains 1, -2, -1. My second row becomes 0, 1, 3. And then to simplify in my third row, I could take row 3 minus 3 times row 1, which would give me -3 plus 3 is 0, 6 minus 2 is 4, and then a 3 plus 9 would be 12. So to simplify a bit further, I could take row 1 and add 2 times row 2, which makes my first row 1, 0, 5. My second row is 0, 1, 3. And to simplify my third row, I can take row 3 minus 4 times row 2, which gives me a row of all zeros. So here we have for our solution, using our first row, x1 is equal to 5, and using our second row, 1, x2 is equal to 3. So as a vector in the plane, we would be looking at the vector x, whose first component is 5, second component is 3. And the image of that vector under this transformation would give us -149. All right. So in this first part of the lecture, we've seen that by looking at the image of these standard basis vectors, E1, E2, E3, and so on, under a transformation T, we can find a matrix which describes that linear transformation, which is called the standard matrix for that transformation. And we've seen examples for how to construct standard matrices for some common geometric transformations in the plane, and how to look at a matrix which describes a composition of multiple transformations acting on a vector at the same time.